Thank you, Regine. Glaciers all over the world are receding and making climate change very obvious to laypersons. So it's an important problem which will mainly contribute to sea level rise at a global scale. Glaciers contribute at present at the same order of magnitude as the ice sheets to sea level rise, so glacier melt is a global issue. More on the local or regional scale, glaciers are very important contributors to hydrology. In the media you often hear the notion no glaciers, no water, and I would like to shed a little bit more light onto this statement. In this talk I will present a new model for global glacier change and runoff, so a new process-based model that is able to calculate the evolution of each individual glacier in the world and its contribution to runoff. So very shortly to the input data, we used the Randolph Glacier Inventory for deriving the shapes of all glaciers in the world. We have about 200,000 glaciers and intersect this Randolph Glacier Inventory with global digital elevation models to extract the surface hypsometry of all the glaciers as well as inventory parameters. Another very important input data to our model is the distributed eye thickness that we have recently derived by an inversion of surface topography for every individual glacier. So we know the thickness distribution for every glacier, and this makes the application of physically based models possible for each individual glacier in the world. So very shortly to the model structure. The ingredients are, as said, a DM and a glacier inventory to derive glacier geometry. And then we use ERA reanalysis data and CMIP5 climate models to get downscaled monthly time series for the past and into the future. In total, we use 14 GCMs that are driven with 3 different representative concentration pathways, so 3 different emission scenarios. This then goes into a mass balance model which calculates accumulation distribution for every individual glacier. We calculate melt using a degree approach as well as an energy balance approach. I will come back to that. The model includes refreezing of meltwater. It also includes a module for calculating frontal ablation, so the ice that breaks off into the sea for marine terminating glacier. And then this allows calculating discharge at a monthly basis for every glacier. After each year, the glacier geometry change, so the advance or the retreat of every glacier, is calculated, and this allows them to get continuous time series for future glacier runoff, as well as sea level rise contribution from glaciers. So just to illustrate this, we have here a profile through a typical glacier with the bed topography and the surface at time 0, as well as the elevation altitude, the area altitude distribution. And if we use our glacial dynamics module, we can calculate the evolution of the glacier geometry and the loss in glacier volume over time and calculate the retreat of this glacier. This allows then to capture nonlinear feedback processes, and this is a considerable advance compared to the presently available global models that are mainly based on empirical approaches. Glacier runoff is calculated as all water exiting from the presently glaciarized perimeter. So we include snowmelt on the glacier, we include rain on the glacier, as well as ice melt, and this gives glacier runoff. For the future, we keep the perimeter fixed. So this is then not a real glacier runoff, but the runoff from the glaciarized headwaters, and this allows keeping the area contributing to runoff fixed and to compare runoff yields to past, future and past. The model is calibrated with consensus estimates of the regional glacier mass budget based on Gray's gravity, ISAT, and direct mass balance measurements based on Gardner et al. 2013, and it is validated against all the measurements included in the World Glacier Monitoring database. So we include annual mass balance, winter mass balance of the glacier, but as also seasonal point mass balances and geodetic surveys. So let me go straight into the results. So we calculate for all glaciers in the world the components of glacier mass gain and glacier mass loss. So for the past, most of the accumulation in gigatons per year was compensated by the process of mass loss. Here we have in orange mass loss by surface melt, and in purple mass loss by frontal ablation, so breakup of the ice into the ocean. So about 90% was compensated in the past, and we get a global glacier mass loss of about 100 gigatons per year between 1980 and 2000. So let us see how this evolves into the future under RCP 4.1, something like a median scenario. We face quite a fast imbalance of the glacier, so we have less snow accumulation on top of the glacier, but fastly increasing melting. So the imbalance is increasing. It remains stable as we go on into the future because glaciers are retreating, struggling to get a new equilibrium with climate, becoming smaller, but the imbalance is still very important. Sea level rise. These are sea level rise curves, sea level rise contribution from the glaciers according to the 3 emission scenarios. So we get something between 80 and 160 millimeters of sea level equivalent. The spread between the 14 GCMs is relatively large, and it overlaps between the different scenarios. How does this compare to previous studies? The results by Marseillon et al. And Radic et al. Are a little bit higher, but the error bars overlap. The results by Giersen and Earlemans 2013 are very similar as ours. So these 3 are the studies that were included in the present IPCC report. Let me look a little bit into uncertainties and the impact of model approaches on calculated sea level rise. So not all glacier mass loss contributes directly to sea level rise because we have a considerable portion of glacier rise that is presently grounded below the sea level for glaciers flowing into the ocean, and this actually reduces the sea level rise by about 10%. This was not included in studies in the IPCC report, but is possible due to the actual geometry prescribed in this study. Another important issue is the use of the MELT model for calculating global future glacier change. So the results presented so far were based on a degree day model. If we use a simplified energy balance model instead, we have quite a bit less of glacier mass loss, which is probably due to a smaller sensitivity of the energy balance model to the temperature change. So let me then come to the title of my talk, peak water. So what is peak water? If glaciers are out of equilibrium, water is increasing because the glacial volume is released from long-term storage. Runoff will increase until the glaciers have shrinked so much that they cannot provide additional water, and then annual runoff will decrease to the initial situation, given that all other components of the water balance remain the same. So there is no problem with water shortage with glacier retreat in terms of annual runoff. However, if we look at seasonal runoff, melting season runoff, we might face a drastic decrease if glaciers disappear because at present they yield their water exactly in the warm period. So when is the timing of peak water? This is a major issue for water resource management because we need to know, are we expecting increase of runoff in glacier-ice basins or decrease? So for the European Alps and glaciers in South America, we are very shortly in front of peak water. So we are right now in a period with glacier mass loss, with increasing runoff, but we expect that runoff will decrease in the next decades. So we can say peak water is expected in 5 to 10 years in these regions with relatively small glaciers and small glaciarization. If we move on to regions with higher glacier coverage, as High Mountain Asia, which has heard about this region by Wouter, we expect peak water at around 2050. But interestingly, also in 2100, we are, in terms of annual runoff, only at the same level as today, which is quite consistent with the results we just heard. Moving up to the north, to Alaska, for example, peak water is expected to occur even a little bit later, around 2060, but with quite strong differences between the emission scenarios. So it is occurring later, according to the model, for RCP 8.5 and a bit earlier for RCP 2.6, which considers lower emissions. Moving to the Arctic, peak water is expected to be even later. So summarizing this figure, there is no problem with annual runoff at the global scale. In my last slide, I'm going back to high mountain Asia because this is really an important region, and I'm going to look at these 5 very large-scale basins and focus a little bit on the runoff regime, or on the melting season runoff. For the melting season, I basically just picked out August. This is an arbitrary choice, but it helps us to look at some simple things. I downloaded total runoff in these catchments from the Global Runoff Data Center, and compared total runoff in August for these basins with the runoff yield from glaciers. So we see that in these 2 basins, with a glaciarization of 2 to 3%, we have a contribution of glacier runoff to present August runoff of 9 to 12%, which is relatively small. So the sensitivity of any changes in the headwaters in terms of runoff will be relatively small. We also see that peak water is occurring around 2050 in the Indus Basin and a little bit earlier in the Ganges-Brahmaputra Basin. In the Indus Basin with large glaciers, we stay above the current runoff yields all over the century and go a little bit down the current runoff yields in the Ganges Basin. If we move up to the north of the Himalayas, to the Sir-Daria Basin with a very small glaciarization, interestingly, we find a very large contribution of glaciers to runoff. This is due because runoff in this basin is also influenced by water losses due to evaporation and irrigation. So we are just comparing what is yielded by the glacier and what is found in the rivers. So here we seem to have a big sensitivity, and moreover, runoff is expected to fall below the present water yields in the melting season. Lastly, the Tarim and the Amu Darya Basin are even more extreme because they are very dry in summer and the glaciers are melting strongly. I don't have time to go into detail here and would like to conclude. So we have presented a new process-based glacier model for calculating the response of each of the world's glacier for sea level rise and local to global hydrology. Peak water is about to be reached for mid and low latitude glaciers, but water shortage is not yet imminent for catchments with considerable glacier storage, and there are strong differences in the response of individual drainage basins depending on their climatic regime. Thank you for your attention.
Thank you. Any questions for Matthias?
Yes, what is the total length of your peak water? When you show the different curves, the top of a relative spike is mostly the elevation difference or the total mass of the glaciers in that area?
I would say it's mainly the total mass, but it's also difficult to say because I summarized all the regions, which includes some 10,000 glaciers. So it will be very much different for catchments with small glaciers and small glaciarization compared to catchments with large glaciers. So I think it's mainly related to the distribution of the glaciers among the individual subcatchments.